All right, I think we'll get started. Hello, everyone. This is Adam Green from ATA Engineering. I'm joined by Tim Palmer, one of our CFD engineers. He's based in San Diego. I'm based in Boston, so we'll be sharing our presentation between those locations. And so today we're going to talk about automating STAR-CCM+, and I know we have some STAR users on the line, as well as I think some Siemens folks. And so hopefully at the end we'll have some good question sessions to brainstorm this a little deeper. With that said, let's look at, if I can make my focus, what we're going to talk about today. I'm really going to talk about three things. One is a quick overview of STAR-CCM+ Design Manager to let you actually automate things from within the GUI. Then a basic JavaScript automation, really using a sonic shock tracking methodology for mesh refinement. And then we'll pass the ball to Tim to really talk about the more advanced things that he's been doing over the last month, with a good example on some bullet modeling. With that said, let's just quickly introduce ATA and who are we. We're a smaller employee-owned business out of San Diego originally, and you can see we have 150 people. And we really have a very highly skilled set of people with professional engineers, over 14 of them, and over 15 years average experience. And so we really tend to tackle the really hard consulting projects for CFD, for analysis, for test and design. And the markets that we work in are primarily aerospace and defense, but some of the others here are new markets for us, but growing continuously. And the themed entertainment one is always quite fun for us to do. Structural work on themed park rides. And a lot of people aren't familiar with ATA and its history, but basically we came out of what used to be STAR-CCM from Cincinnati, and during the 70s and 80s and 90s there were a lot of shifts in the market and various people purchased STAR-CCM. And in 2000, out of that, ATA Engineering was born as the test and analysis vision of STAR-CCM. Then became ATA Engineering. And since then we've grown considerably, opening a new office in LA in 2005, 2007 we opened a Denver office, 2009 a Huntsville office, and then in the last year we opened a Berkeley, California office. And so in basically 2009, really because of our heritage back to SDLC and Unigraphics and NX, we were a very early partner for Siemens selling NX and CMAP and Nastran. But last year in 2018, we extended that to full sales and support for STAR-CCM+ and HEADS. And you can obviously tell that those pretty much gel with today's presentation. And really, the list of things we do, I mentioned it already, we do full design work right the way through analysis and test. And test is one of our biggest divisions, doing a lot of ground vehicle tests through to really any tests that are required for pulling data for analysis in the field. Here are our offices scattered around the US, but mostly in areas of an aerospace focus. And so you can see Huntsville, DC, San Diego, and San Francisco are logical places. And so let's talk a little bit about STAR-CD. And this one, I tried to find as many cool animations as I could fit on one slide, so we weren't spending too much time on it, because most of the users we have online either know STAR or are at least familiar with it. But really, what makes it special is really first of all, its productivity and just advanced usage. But secondly, its flexibility to do pretty much most problems that you can think of can be handled by STAR, from turbo machinery to DEM on the top right there, to multi-phase, the one in the middle with the car for de-icing of a car going down the road is quite an extreme problem from a meshing perspective and a physics problem. Now on the right, multi-phase in terms of VOF, fluids modeling, is also a strong forte for STAR. So it's really strong in many, many areas. And so what I'm going to talk about first is really the simple part of today's presentation, and that's automation from within STAR-CCM+, from within the GUI using Design Manager. And so some years ago, when CD.co developed Optimate, they had two products within STAR-CCM+. One was Optimate and one was Optimate Plus. And Optimate let you do sweeps of parameters automatically, so that you could do simple parameter sweeps to look at multiple models. And then if you wanted to do design exploration, you used Optimate Plus, and both of those will cost extras. But in the last year, Siemens have kind of redone that a little bit, and now Design Manager, which used to be Optimate, is now built into STAR-CCM Plus at no cost. So anyone out there using STAR-CCM Plus can literally do what you're gonna see now with their current license. And so basically, it integrates into the GUI, so it makes it very easy to use, and it really automates parametric sweeps. And the variables can be boundary conditions, they can be geometric, they can really be anything that you can define in STAR to sweep through and look at variations in performance. Obviously, that depends on the nature of your work, but could be geometry, like this one here in the turbo machinery, but really gives you great flexibility. And then if you say, well, once you've gone that far and you're able to do automated sweeps of a certain parameter or variables, then it's quite straightforward to move on to actually use STAR Innovate, which contains the solver and the technology found in the STAR-CCM Plus HEEDS tool to do much more advanced design exploration. And instead of running maybe less than 20 sweep points, you can run hundreds of points from a design space in the millions. And so STAR Innovate is what used to be STAR Optimate Plus to do full design exploration. And so this kind of breaks down really the goal here, that it's easy to use, and we've kind of said that already, but the Design Manager piece lets you do it with no additional licenses, and then adding Innovate really lets you jump into the HEEDS world of advanced design exploration. And so this is actually an animation that I'm going to walk through, but it's actually from LR in this case. I hope you can all read the text. LR stands for Lloyd's Register, which is a shipping group out of the UK. And they use Design Manager to really just run through a sweep of ship hull design shapes, where the hull design is the same, and the vessel velocity is the parameter to vary. So in this case, a project is set up, the variables selected. It's going to be a sweep of velocity, and we're going to choose 5 different speeds, 8 through 16 knots to run the vessel at, which could be run totally automatically. And then once you've done that, this is really where it gets pretty nice, is that you get a table of all of your designs based on each of the variables you've chosen. And then you can set up post-processing to view each one very simply. So you can either click on the table to highlight the view on the right, which is set up by you as well, or on the graphs to highlight each point. And this point's interactive, so that if you change the view in one, and then move to another point, you can see how it compares. In this case, how does the bow wave get impacted by the speed of the vessel? And then it actually gets even better than that, in that you can pull up two views of 2 different design points in your view, and actually compare them. And the views will stay synchronized, so that if you move the graphics in one, it'll move it in the same viewpoint in the other. So when you're doing A to B comparisons of geometries, this is pretty valuable to be able to easily pull views and data out of the different points very easily, very quickly. So that's about it for Design Manager. It's very simple, and everyone really should give it a shot, because it's included and can really help with your productivity. And so really the next step is blending some more advanced field functions in STAR-CCM Plus with JavaScript. And this example is actually pulled off the STAR-CCM Plus support portal. It used to be the Steve portal, and so this example is in there, and we're going to provide links to this example on our webpage for the recording of this webinar, so that people can go and pull that data set and actually try it out, as we're going to show you here. So basically, the example here is the idea of doing some mesh refinement based on tracking a shockwave. And so mesh refinement's not a new thing, but it's certainly not everywhere in CFD. And STAR-CCM Plus doesn't have it built into the solver by default. So this lets you really home in on a shockwave to understand the makeup of it, and really getting a good mesh density around the shock. And so when you look at this list of things that are done here, it feels a little intimidating, but it's really not, because this can be automated. So basically line 7 here, you can see that all of this gets automated into a loop. And so when you look at the first one, you create a coarse mesh. You really create a field function in STAR, which uses density of the gas to identify where the shock is. And then using other field functions, you do some work to make sure that the region around the missile in this case is not refined, and also that the cell size is normalized effectively against the density, because you're looking at a gradient across the cell. So those first, well, really the first 5 items there are really field functions to help you home in the field function refinement table that you want to use to redo the mesh. And then you remesh it, and you look at the answer, and this can be done manually as well with items 1 through 7. But then if you automate it, life gets much easier. And so this is some snippets from the Java, and really it's not much longer than this, but this, and STAR can record this Java. So basically, most people who are doing JavaScripting with STAR will start some activity and record it, and then go in and edit it manually. And it's actually a nice way to learn Java. I think Tim will talk about that later, that's what he's done. But nonetheless, this is part of the Java. And when you look at this, this basically says that the input data that we've written it's going to actually do 20 mesh refinement steps, and each of those steps is going to run for 150 iterations, but the total time steps is going to be 5,000. We set that in the Java. And then these are the things that are recorded from the field functions and the meshing that really use the STAR API to pull in the arguments that you need, and it's pretty straightforward. So even though this looks a little intimidating if you don't know Java, this was actually recorded by STAR while it was running, and the user could easily record it. And then the loop to actually do the mesh refinement is pretty straightforward. For the first run, it basically says if this is the first time around that loop of 20, then let's remesh and run, and otherwise let's just run, and then it runs to the end of sim runner at the bottom where it actually stops. And so that's pretty much it. It's literally 100 lines of Java code. It's certainly not very much. And so when you look at how that manifests itself in a result, this is the video of this thing running. And this would be the first mesh, and this might be the first, the first 100 sweeps get to this point for a Mac number. And then when you run it, you can watch the mesh refine. Remember that it's refining every 20 steps. And so you can see how the mesh tracks the shock and really does a much better job of defining the shock and making sure there's enough mesh resolution across those high density gradients. And this, I find this intriguing to watch, the way the cells in some areas seem to kind of wane a little bit as they move along, and in the end it kind of stabilizes. So if we look at the residuals for that run, you can see, and I hope you can all see my mouse, but basically each one of these is one of those mesh refinement steps. So between here and here is 150 iterations, and there's 20 altogether down to here. And to be honest, the version that's on the STAR portal doesn't do as many iterations as this. It doesn't do 20, but I wanted to see, how many was the right number to do. So I did, clearly you can see I did much more than I needed to do. And certainly if I'd done 6 mesh refinement steps, I probably would have been adequate to get where I needed to go. You can see that the residuals are pretty much, get to a good level. And if we let it run out from say 1,000 sweeps, just let that carry on, we'd have probably got a similar result. So it might be that these last 15 or so mesh refinement steps weren't needed. But nonetheless, it does give you a good clue as to how the convergence can be impacted. Certainly, the 7th mesh iteration would give you a much better answer than this first one. And who knows what it would have done if we just let that run to convergence. So with that, I'm going to pass the ball to Tim.
All right.
Are you there, Tim?
I am. Can you hear me?
I can, and you now have control.
Okay. Thank you very much. Good morning, everybody. Maybe it will go. There we go. So Adam was just giving us a pretty good overview of some of the other automation capabilities that are within STAR. I'm going to talk a little bit about what you can, some of the finer points you can actually do with the Java macro scripting in particular. Macros can be generated a couple of different ways in STAR. The first, as Adam mentioned, and the easiest, is just record yourself doing things, and that will automatically generate a JavaScript that you can then run later as a macro. And that control is in the upper toolbar here, the ones I've highlighted in the red box. Obviously, circles record, play, etc. And that will get you most of the way there. But if you're looking to do something that's you need a high amount of control over your simulations, or you're going to be changing a whole lot of particular parameters, then you might have to do some manual editing. And STAR gives you some tools with that as well. You can actually access the STAR Java API library reference through the help menu in the STAR user interface. And it'll bring up a page in your web browser that looks like this picture here, where it lists all the various classes and methods that STAR uses to accomplish all the stuff that it does in the background. This is particularly useful for any reference to reference any class or method that's not captured by the recorder. One example of that, and we'll see that today, is any method that writes to the output window and has information that you need in order to control your automated run, because that will not be automatically stored by the macro recorder. So that would be something you'd want to manually add to whatever script is generated when you record yourself setting up a run. And so we'll look at sort of how these two things work today with a quick example that I call ballistics through the centuries. Basically, the idea here, we're going to be showing how you can automate an analysis process that features changes in geometry that takes advantage of STAR's geometry and meshing pipeline that sort of makes it efficient to run all these different cases. We're going to look at three cases today: an 18th century 58 caliber musket ball, so Revolutionary War times; 19th century, so Civil War time 58 caliber Minier ball, which is getting closer to the modern bullet design, but not quite there; and then the modern NATO 5.56 round, which is a 2.24 caliber. All of these things, I'm going to try and demonstrate the automated update and configuration of solver settings so that you can run the same simulation, but looking at these different bullet designs from over the past few centuries. So as I mentioned, three cases: musket ball, Minier ball, and projectile. I've given the information here for your reference for what we're going to be running. One important thing to note is the Minier ball and the NATO 5.56 round are spin stabilized, and so I have assumed a certain barrel length and twist rate based on firearms that tend to fire those rounds, but the musket ball assumes no spin. I'm going to be using a time-accurate simulation just so we can get some cool animations and see how the drag and the flow field around the bullet develops when it's first expelled from the muzzle. So using something like the shockwave mesh refinement that Adam was just talking about, you can certainly do it, just adds more computational cost. The other thing too is I want to calculate the forces, and so that lets us use, or that requires us to use STAR's dynamic fluid body interaction model, where you can compute the fluid forces on the bullet and then have those fluid forces actually affect the bullet trajectory and velocity. And so the bullet in motion will be captured by an overset region, which is the sphere that you see in this inset around the bullet, and it'll be flying through a coarser background region, although I have put a refinement volume in what I call the flight corridor down the center, so that the cells in the flight corridor are roughly the same size as the outer cells of the overset region, just to make it easy for the overset calculation. That's how we're going to set up the case. Now, to do this, we're going to take advantage of STAR's pipeline-based organization. And generally, when you're setting up an automation analysis task like this, you're going to want to set up one simulation case using that Java macro record feature to basically capture all of the main things that you're going to be changing from case to case. And that'll include things like mesh settings, boundary conditions, reports. I mean, you have control over reports, monitors, plots, scenes, and field functions as well within the Java, but best practice would be not to touch those when you're doing one of these large analysis sweeps. just because you want your post-processing to be roughly the same in order to be doing an apples-to-apples comparison towards the end. So you really only want to be changing the pre-processing stuff like the mesh settings and boundary conditions and initial conditions as required. And you can take advantage of STAR's parameters feature as much as possible for this variation. And so one that I'm going to talk about in today's topic is this max length scale parameter that I use to control specifically the overset region sphere size based on the size of the bullet that we're modeling. So all this, as I said, takes advantage of STAR's pipeline-based organization for the geometry and meshing. Specifically, the geometry operations manager, this operations node here, contains a lot of different options of operations for preparing surfaces, operating parts, generating meshes. And all of those operations are executed in order and can be executed with a single command at the end of your JavaScript, so that any change you make in the parts themselves will then be reflected in your eventual mesh. For today's example, in order to do this and prepare the new simulation for that execute all command on the operations, we need to do a set of tasks first. And so I'm going to list those out now. The green ones are ones that I recorded myself doing when I set up the first simulation. The blue is the one that has a bit of a manual component. And so we'll go into that in a little bit of detail. But the first you obviously need to do if you're changing your geometry is load in a new geometry part to replace the one that you're analyzing. In this case, we'd be loading in a new bullet. And then the second step would be to import that new bullet that we've loaded in into a separate CAD model. So you can see here in the project view, we have one CAD model already, which is what we use to create our background region. So the background part, the flight corridor refinement volume, and then the overset sphere volume with the design parameters to define all of those. For the bullet, we're going to need to import it into a separate CAD model because of the third step, and that is to take advantage of STAR's built-in CAD modeler and extract the solid properties of the bullet design and store them for later use. Obviously, in the a couple slides ago, you saw the different types of bullet designs, very different geometric shapes, very different sizes. And so we can use STAR's CAD modeler to pull out things like the center of mass for that bullet, the moment of inertia, the size, which we can then use to sort of inform the geometry of our overset and our background region. And then the manual step is that storing those properties so that we can reference them later in our automation scripts. Because the fourth step is we need to update the DFBI properties with the solid body properties. Again, center of mass, moment of inertia, things like that. So we need to store them so we can reference them for that portion of the script. The other thing you'll see in some animations a little bit later, this bullet is moving through an overset region, and as you can imagine, it's moving very fast, moving over a great distance. So if you were to zoom out so that you can see the entire flight trajectory, you wouldn't be able to see the flow field around the bullet. What STAR will actually let you do, especially with DFBI simulations, you can fix your views and tie them to a certain reference frame or coordinate system. In this case, we'll have a scene set up that is referenced to a moving coordinate system that will always follow and be centered on the projectile. And so we'll update that center of mass, or update the coordinate system to point to the center of mass location of the projectile for the initial run. The sixth step, which is in this automation script, or you might want to do if you're doing a geometry refinement study where maybe the parts are coming in and they're not coming directly from CAD as all one surface, maybe have some additional surfaces, either because you scan them, you're bringing them in from a separate FEM, like if you did structural analysis on it, you're bringing in the structural FEM, etc. You can combine all those surfaces into a single surface to make it easier for referencing. We're not going to go over that today because it doesn't actually need to be done in this particular application. And then the seventh step is to update the CAD parameters. So this is, we've brought in our new geometry, we've gotten the information out of it we need. Now we're going to get ready to do the execute all and update all of our geometry and our mesh. So we need to update that max length scale parameter and then update the parts that are associated with it. We need to update the part that we're pointing to for the subtract operation, this square that looks like it's got a hole in it, to point to the new bullet. We're then going to delete the old bullet and clear the previous solution so that we can reset where our overset region is. And then finally, we'll execute all the operations in this operations node. So we'll do the subtract of the bullet from its overset, and then we'll mesh the background, followed by meshing the overset region. I'm going to go into each one of those steps in a little more detail now, starting with the loading the new geometry part. And in this case, we're going to take the example of we're starting with the round musket ball and switching to the Meunier ball. I've got a snippet of the code from the Java macro that I recorded within STAR. It basically is generated from the import surface mesh menu option in STAR. If you were to do this manually, this is the set of Java commands that is behind your mouse clicks. The one that's really important from an automation standpoint is this import CAD part, and you can just feed it any argument for a file path. And this is, if you had it in a for loop, this is the part that you would update. That argument is what you would update each iteration of the for loop to sweep through those hundreds of geometries. This other part here I have is optional. This would be if you wanted to create a separate geometry scene for each part. Probably not if you're doing hundreds, but if you're only doing a few, then maybe. And this is generated by way of the macro when I did it at the time. But you can also, if you were to do this yourself, unselect the option in the import command that makes this come up. But that's the general command. And what you'll see when you run this, oh, it's getting hidden, I guess, behind the text. But you can see the tail end of Meunier ball here showing up in the parts list. And so that's been imported and is the result on the project tree of running this snippet of code. So the second step then is to take that Meunier ball part that we just added and bring it into a separate CAD model, this CAD model 2, again, to sort of prepare for extracting the solid body properties. And again, this is another thing that you can record. So you just, while you're recording your macro, you would right click on the part, edit in 3D CAD, and it would, STAR will automatically add all of these commands that you see here in this Java snippet. So all this is equivalent, like I said, to the edit in 3D CAD on a given part. And when you're automating and putting this in a for loop, you would just update the argument for the get part to point to the part name that matches whatever your the name of the CAD file is that you just brought in. So in our case, we just brought in the Meunier ball parasolid. The part that comes in has the same name, Meunier ball, and so you update that argument in your for loop, and you're good to go. So then the next step, and this is the one that has a mix of both recording and a manual step, is to export the solid body properties of this bullet that we just brought in and store them for use. And so when you're recording the macro, if you were to do this manually in the CAD modeler, you'd right click on your body, you would go to body and properties, and it would spit out all of the solid body properties in the output window down here, things like center of mass, mode of inertia, and then you can see the geometric extents, min and max. When you're recording the macro, those values don't come out. The thing that does end up getting stored contains a bunch of extra information, is not easily referenced. So you need to do some manual adjustment in order to actually store those for later. And so to look at what the JavaScript spits out when you're doing this and recording it in the macro records everything marked by the first sort of grouping here up to the end of the units. And it would store it in that body prop _0 class known as a neo property within STAR. That contains a couple of different types of variables. One is what's called a hash table in Java. You can think of it as basically a structure that has a set of keys with a set of data associated with each key. And it's stored as one entry in this body prop _0. So we want to manually store it so it can be easily referenced to the rest of our script. And so I added this line manually, neo property body prop table equals, and then get the property 1, that particular entry, which contains everything from center of mass, moment of inertia, geometric extents, etc. And so we've now stored that. And again, that was manually added, whereas the rest of this was all recorded based on the actions that I was doing in the simulation at the time. So now the next step is to update the DFBI properties with the information that we just stored. And this one is mostly recorded, although there are actually some manual parts that I've added or had to change. Because if you're recording yourself doing this in the macro recorder, you would click on the different properties shown here under the DFBI node. So take for instance, center of mass, and you would record yourself changing that value from whatever it is to some other value. And then when you go to actually generalize your recorded script to put into a for loop to run this hundreds of case analysis set, you would need to change that value to something that would be updated within your for loop. So in this case, that body prop table that we just stored, and we would be updating every time we go through the for loop with a new geometry, I've just passed into the argument for updating the center of mass. So center of mass, set the coordinate units. This basically says set it to meters, and then here's the location, getting the vector from the body prop table that we stored earlier. Same thing with the moment of inertia. You record yourself updating the moment of inertia values so that you get this moment of inertia get components, set components command. And then you would manually add in this set here, double vector, new MOI, all of those, so that you point at the body prop table that you're storing and getting the individual components out, storing, and then programmatically updating them with a variable. So that's an example of another example of mixing both the recording of your Java macro as well as sort of adding some manual updates to extend it to a larger data set, like a for loop automation. And then I had down here the case initial conditions, and this would be another example where these numbers, so like the velocity, set component, the mass, etc., that you would want to point to, or you would want to use a variable from your for loop to dynamically update those throughout the set of cases. But those are the numerical values for the Meunier ball that we're using now. All right, and then the next thing, now that we have the center of mass properties and we're using them to dynamically update settings of the solver, we're also going to want to recenter the moving reference frame on the new bullet that we're bringing in. So you can see here a picture of the original musket ball with the moving coordinate system, this view motion coordinate system highlighted, centered on the musket ball's center of mass. The Meunier ball is significantly larger and longer, so its center of mass is going to be different, and we're going to again use the body prop table that we stored earlier to set the coordinates of our vMotion coordinate system to the center of mass of the new bullet. And that's, again, you can record yourself doing this, and then just go in and change that one entry based on this generalized script that you're going to be building for this hundreds of case analysis set. All right, preview number 6, because again, it is optional for this particular case. We're going to go to 7 and 8. In this case, we're now updating our CAD parameters as well as the subtract operation parameters, specifically the parts, and then executing those. And we're using the lengths that we got out of the solid properties check, adding a little bit of code to compute what the max length scale is, and then updating that design parameter, get design parameter manager, get object max length scale, and setting it to the max length that we calculated. And so what this does in this automation script is we bring in a new bullet, we figure out how big that bullet is, and then we resize our overset region to adequately capture the flow around it based on the size of the bullet. So there's a diameter ratio here that's basically a multiplier on this max length scale that sets the diameter of our sphere for the overset region. So as you bring in a longer bullet, and we'll see this a little bit later, as you bring in a longer bullet, you'll see the overset region expand based on the larger, the higher length of the new bullet. All right, and so once you've updated those parameters, you've got the new part in the subtract operation. We want to delete the old part, reset the solution so that in this case, the DFBI body moves back to its initial location, and then get rid of the old part so that when we run this loop again, all of the names that we're referencing haven't changed. Because what STAR will do by default, if you don't delete the old part and rename things, is it'll start adding integers on the end of these names. So you can obviously take that into account in your for loop programming. I find it just easier to delete the old parts since you're not using them anymore. And then we run that execute all command, which is this final command here in the Java macro. And again, all of these pieces of the code were recorded by the Java macro recorder built into STAR as I was doing it, setting up the first simulation case. And as we run that, you'll see the bullet will be brought in. The minier ball, as I said, is bigger than the musket ball. The view motion coordinate system has moved to the new center of mass, and you saw the overset region grow based on the larger length scale of the minier ball compared to the musket ball. And so that's the result of this automation script to update the geometry dynamically, to automatically remesh it based on properties that you're getting from STAR itself. So you're not having to compute all of these different properties and store it in a giant spreadsheet or a giant table or array or structure ahead of your for loop. You can actually get this from STAR and then dynamically update it using the Java scripting that's available within STAR-CCM+. And so if we do that and we go ahead and run these simulations, just so you guys have some pretty animations to look at, we'll look at each of the three in turn, starting with the musket ball, where you can see a detached bow shock along with some additional shocks and compression waves on the trailing half of the musket ball as it moves through the air. And these scenes were set up ahead of time using STAR's automatic file save feature for these scenes to write them out, and then we can animate them later. And the fixed frame, so the inset here where it's fixed on the bullet, that's the one that takes advantage of that view motion coordinate system so that you can always lock to the bullet and visualize the flow field. So again, musket ball, you've got a slightly curved, significantly detached bow shock. For the minier ball, that's properly spin stabilized. It's still slightly detached, but the curvature is not as significant. And you'll also notice the set of compression and expansion waves around the ridges on the trailing cylinder of the minier ball, which I thought was pretty interesting. And then finally, the NATO 556 round, which you'll notice in the flight mock, it's significantly higher, and that's because that bullet was launched at Mach 2.2 instead of around Mach 1 from the muzzle. But you'll see the same sort of shock structure. In this case, you can actually see some unsteadiness, and I'll talk about that in a minute here, in the shadow graph in particular, looking at the series of compression and expansion waves around the bullet itself. But all of these simulations, basically for all three of these bullets, you run the script, you bring in the new geometry, update all of your settings, and then execute your operations to rebuild your mesh with the new geometry, and then run, and you can spit out all of these same post-processing views with each individual bullet. And then finally, just to kind of close the loop on comparing the performance of these different ballistics through the centuries, I've got a comparison of the bullet drag coefficients. Blue is the musket ball, red is the minier ball, and green is the NATO. And as we'd expect, the drag coefficient for the minier ball is better than the musket ball. The NATO drag coefficient is actually significantly higher, and I'll talk about that in a moment. Looking also at how the bullets retain the kinetic energy on the figure on the right, you'll see that the minier ball outperforms, again, the musket ball as you'd expect because it's more streamlined, spin stabilized, maintains more kinetic energy as it flies. The NATO loses proportionately more of its kinetic energy over the same time period. And that actually inadvertently demonstrates the importance of proper stim stabilization for these bullets for maximum bullet performance. When I was setting up the NATO simulation, I used a representative barrel length and twist rate from the range that was given as standard for NATO 556 weapons. And turns out that that variation is based on the specific characteristics of the bullet itself. And so the twist rate that I chose didn't match the bullet that I chose as well. So it's actually slightly unstable, and that's the reason for the higher drag coefficient. So pretty interesting. But the other interesting thing to look at is because the bullet's going faster, it's actually maintaining kinetic energy versus distance better than the musket ball. So it's still better performing in that regard, even not completely spin stabilized. So I thought that was pretty interesting. So with that, I just wanted to summarize what we've talked about today with the automation. You've seen throughout Adam's and my talks, STAR-CCM offers several avenues to automate design analysis over a myriad of products. If you remember Adam's sort of snapshot video slide showing all the different applications that STAR is applied for, these automation methods can be applied to any of those products. The design manager that Adam talked about provides one potential built-in, or one potential method that's built into STAR for efficient exploration of a parameterized design space. And it has some optimization capability and analysis capability, as you saw in the video showing the comparison of performance of these different parameterized designs. But it's scalable to even more advanced optimization methods using optional add-on packages like STAR Innovate or HEEDS. If you want a little bit more control over the automation that you're doing, the Java macro functionality built into STAR gives you that capability. It's highly customizable, and it's easily generated with the macro generation recording feature, as well as just direct editing using the API reference. And when I say easily, as Adam sort of alluded to earlier, I didn't have much experience with Java when I first started using STAR, and in fact, so far I've only used it a few times to do this kind of Java macro automation. But I have, as long as you have some basic programming knowledge, specifically with object-oriented programming, it's pretty easy to pick up and figure out how to work with it, because the recording feature gets you probably 90% of the way there, and the rest of it is just basic programming for the most part. And so we showed today a couple of applications, one being this automated analysis process for a large set of designs with the 3 bullet examples. And then the other is the one that Adam talked about, where you can dynamically update mesh or simulation parameters to improve accuracy or efficiency when he showed the automatic refinement of the shock case. So hopefully you guys got a little bit out of this and saw something interesting, and we'd be happy to take any questions.
Excellent. Thank you, Tim. That was great. So everyone's been on mute so far. So what I'd like to do, Jonathan, if you can take everybody off mute, and if anyone's got any questions they would like to ask, now is a good time.
Yep. So I have kind of updated the meeting so that if you go to the bottom left-hand corner of your screen, there's a little unmute button. You can unmute yourself there if you have any questions that you would like to ask. You can also certainly ask questions in the chat if you would rather submit questions that way. But Adam and Tim, very, very cool presentation.
Excellent. Okay, anyone got any questions in the audience?
Before we go, Christoph, to answer your question in the chat, the initial conditions, I did not. So the initial conditions you saw were updated in the script there. The velocity, well, I guess the initial conditions for the background is just still air. Because it's a DFBI simulation, the initial conditions for the velocity is updated in the DFBI setting. I don't know if I still have control, but anyway. And then the spin rate is also there. So that's where the initial conditions were updated. You would do that with the for loop. Those were the parameters that you would want to store in the array, because you're going to need to store like muzzle velocity or twist rate, etc. And then as for refining the mesh, no, in this particular case, I did not refine the mesh. All the mesh settings were kept the same. However, you can programmatically refine the mesh if you want to. For example, in the mesh operation, the base size setting, as well as target surface sizes, any of those settings can take variable arguments or parameter arguments. So you could feasibly set the base size to some fraction of your max length scale of the bullet as a parameter, and then when you load in the new bullet, the base size for that new mesh would automatically update as well. So that can be done. Did that answer your question?
think that was in chat. So, Christoph, we assume that answered your question. All right, we appreciate it, everyone. Thank you for your time today. I hope that was pretty comprehensive about what STAR can do on the automation side. And after today, this will be on our website as a recorded webinar, so you can watch it again if you want to, or show it to other people. And also on that page is going to be a link to some of the resources on the Siemens site as to where to find some of these examples. Not so much on Tim's work because that's ATA, but on the Siemens work, the shock version. That's actually from the Siemens support portal, and we'll provide a link for you to find that. So thanks again, everyone. We'll appreciate it, and we're going to close the meeting.